Section 9.4, Partial Fractions. What is partial fraction decomposition? Well, to write a sum or difference of rational expressions as a single fraction, we bring them to a common denominator. All right, so in this section, you may see this phrase, rational expression. That just means you're dealing with a fraction. Okay, so what we've been used to in our math past is when we add or subtract two fractions, to do that we have to get a common denominator. So let me give you an example. If I had 1 over x minus 1 plus 1 over 2x plus 1, okay? Both of these terms, 1 over x minus 1 and 1 over 2x plus 1, they're rational expressions. They're fractions, okay? They're complicated because they have a variable, but we can add these guys and combine them into one fraction. To do so, we have to get a common denominator, okay? So what we would do here, okay, we would bring it to one fraction. To get the common denominator, the easiest thing to do is take your denominators and multiply them together. So the common denominator here would be x minus 1, that quantity, times 2x plus 1. And then you'd have to adjust the numerators. So you would go to each term and you'd say, okay, well, if I look at this first term, 1 over x minus 1, it doesn't have the correct denominator. It has the x minus 1 piece, but it doesn't have the 2x plus 1 piece. So in order to get the correct denominator, we'd have to multiply the bottom by 2x plus 1. But if we do that to the bottom, we also have to do it to the top, okay? If you are multiplying this quantity 1 over x minus 1 by 2x plus 1 over 2x plus 1, you're really multiplying it by 1 because any quantity divided by itself is 1. So you're not changing the original term, okay? So if you multiply across the bottom, we do end up with the correct denominator, but to multiply across the top, the new numerator is going to be 2x plus 1 times 1, which is going to be 2x plus 1, okay? And then we have to adjust the other term, okay? We will keep the plus sign in the middle, okay? So this plus sign will go here, okay? Then we adjust the numerator of the other term. 1 over 2x plus 1, it does not have the correct denominator. In order to achieve this, we need to multiply the bottom by x minus 1 because we already have the 2x plus 1. If we multiply the bottom by this, we have to multiply the top by x minus 1. Okay, because again, x minus 1 over x minus 1 is 1. You're not changing the original term. Okay, so if you multiply across the bottom, you will get the correct denominator. Multiply across the top to get the new numerator. This is going to be x minus 1. Okay, and so then you can go ahead and you can simplify the numerator. You can just add like terms. So 2x plus x is going to give you 3x. And then 1 minus 1, those guys will cancel. So you're going to get 3x over x minus 1 times 2x plus 1. Okay, so this was just a refresher of what you've done in your math past, how to combine two fractions either through addition or subtraction. You do have to get that common denominator, okay? That's what we're used to, okay? Taking two fractions that we're adding or subtracting and combining them into one. What partial fraction decomposition is, it's the opposite process. You are given the single fraction and you have to break it down into the two fractions that you add or subtract to get that one fraction. Okay, so if you read here, it says for some applications of calculus, we have to reverse this process. That is, we must express the single fraction as the sum or difference of the simpler fractions. These simpler fractions are called partial fractions. We will learn how to find them in this section. Okay, so what partial fraction decomposition is, okay, an example would be what we just did, but reversing the process. You would be given the single fraction. You would start with 3x over x minus 1 times 2x plus 1. And in all honesty, this denominator would probably be multiplied out, okay? But you would be given this single fraction, like I said, probably with this denominator multiplied out, and you would have to break it up into the original fractions. You would have to come up with, well, this is the same thing as 1 over x minus 1 plus 1 over 2x plus 1. Okay, so you're reversing the process. Okay, so I'll draw an arrow here. We're going in this direction. Okay, so this is what partial fraction decomposition is. Okay, you're taking a single fraction and you're breaking it up into two simpler fractions that you either add or subtract to get the original fraction. Okay, this is something you're going to need to know how to do for calculus 2. Okay, all right, so let's talk about some terminology that you need to know in order to do this. Okay, we're going to talk about what a repeated factor is. Remember, when you factor something and you end up with the factorization, factors are the things that you're multiplying together. A repeated factor is a factor that appears in the factorization of a polynomial more than one time. So in other words, a repeated factor has a multiplicity greater than 1. Okay, so for example, if I go out here and I say, I don't know, x plus 1 times x plus 1. Okay, this is some quantity that's been factored. It has two factors, x plus 1 and x plus 1. They're the same factor, so x plus 1 is considered to be a repeated factor because you see it in the factorization more than one time. Okay, so if I use this phrase repeated factor, it's just a factor that appears in the factorization more than one time. Okay, another term you're going to need to know is irreducible. A polynomial f of x is irreducible over the real numbers if it cannot be factored as the product of polynomials g of x and h of x, where the degree of g of x and the degree of h of x are both less than the degree of f of x. Okay, so basically, kind of a simpler way to think of the word irreducible is you can't break it down further. It's something that cannot be factored again. Okay, so like when you've learned to factor in the past, you're always told to factor completely. You want to factor each part until you can factor no more. So for example, if I look at what I wrote down up here and I said x plus 1 times x plus 1, both of these factors do not break down further. You can't factor them again. Okay, so this is considered to be irreducible because you can't factor any more. Okay, so when you're doing something you always want to factor completely, that's basically saying you're factoring until each of the pieces is irreducible. You can't break it down again. Okay, all right. Last thing we're going to do before we start doing examples of this partial fraction decomposition, we're going to talk about the different cases you can see. Okay, it says we will investigate the following 4 cases of partial fraction decomposition for a rational expression p of x over q of x. These cases are applied only when the degree of the numerator p of x is less than the degree of the denominator q of x. Okay, so that's important. That's why it's in blue. Cases 1, 2, 3, and 4 apply only when the degree of the numerator is less than the degree of the denominator. Okay, if we have the reverse situation where the degree of the numerator is bigger than the degree of the denominator, we'll talk about that down here. Okay, so let's go through the 4 cases where the degree of the numerator is less than the degree of the denominator. Okay, case 1, the denominator is a product of distinct linear factors. Okay, we will go through this, okay, but in a nutshell, distinct means your factors are all going to be different, okay, and then linear means that your factors, the highest power of x that you see in each factor is the first power, okay, so your factors are going to look like mx plus b, okay, and they're all going to be different, okay. Case 2, the denominator is a product of linear factors, some of which are repeated. Okay, so in case 2, you're still dealing with linear factors. So the factors, the things that you're multiplying together, they're linear. The highest power of x is 1. They look like mx plus b, but this time they're not distinct. Okay, you may have repeated factors. Okay, so some factor that appears in the factorization more than one time. Case 3, the denominator has irreducible quadratic factors, none of which is repeated. Okay, so in case 3, the denominator is going to have quadratic factors. Those guys look like ax squared plus bx plus c. They're irreducible, which means you cannot factor them any further, and they're also not repeated. The last case, case 4, the denominator has a repeated irreducible quadratic factor. Okay, in case 4, you're still dealing with quadratic factors, ax squared plus bx plus c. They're still irreducible, meaning this quadratic quantity cannot be factored further, but you are allowed to have a repeated factor. You may see the same factor twice in the factorization. Okay, so now let's switch gears and talk about what happens if the degree of the numerator is bigger than or equal to the degree of the denominator. That's this last statement in blue. If the degree of the numerator p of x is greater than or equal to the degree of the denominator q of x, you first have to use long division to divide q of x into p of x. Okay, so you're going to have to use long division, and then after that you'll be able to apply one of the cases, either 1, 2, 3, or 4. Okay, so this all may seem a little confusing right now, but we will go through each of the cases and do examples.